So this is ELC 131, Circuit Analysis 1, and I want to do just a short discussion of electromagnetic devices as related to audio. And the first device we'll look at is a dynamic microphone. Figure 1 shows us a picture of a dynamic microphone and a cross-sectional view of that or through that dynamic microphone. And a dynamic microphone works according to the following principles. Of course, sound pressure waves, which are compressed and uncompressed air molecules, strike the diaphragm and move the cone in and out. And that cone is attached to a coil of wire. And of course, the sound pressure waves move this coil of wire in and out of the lines of force of a permanent magnet. And of course, anytime we have relative motion between a current carrying conductor and flux, we induce a voltage. So voltage is generated across the coil that varies according to the frequency and the intensity of the sound waves that strike the diaphragm. So this is how we change acoustical energy into electrical energy, by moving a coil back and forth inside the flux of a permanent magnet. Now, it's nice if we've got some audio from voice or from acoustical energy. However, we all know that we need to have some electric guitars and or an electric bass to go along with our singing. So figure 2 shows us a top view of an electric guitar pickup. This is actually a bass guitar pickup because there's only 4 strings. And then, of course, it shows us a cross-sectional view through what's called a single coil type pickup. Now, the construction of this, of an electric guitar pickup, is that there is a coil of wire wrapped around a permanent magnet. Now, as you recall from the previous discussion of magnetism, that magnetic flux or magnetic lines of force can travel through steel or iron more easily than they can pass through air. So as the string vibrates back and forth across the top of this coil, we see that the magnetic field gets bigger or smaller depending on whether the string is directly above the coil of wire. So we've got this magnetic field moving up and moving back down. And of course, anytime we have relative motion between flux and a conductor, we will induce a voltage. So a voltage is generated at the 2 terminals of the coil, and again, that voltage will vary with the frequency of movement and the intensity of the movement of the steel string. And of course, we've used the microphone to convert acoustical energy into electrical energy. We've used the electric guitar pickup to convert the motion of the steel string into electrical energy. And we need to convert that electrical energy back to sound pressure waves or compressed and uncompressed air molecules. So figure 3 shows us a cross-sectional view of a large cone speaker or loudspeaker. And the construction of this device is that there is a circular magnet that surrounds a coil. And as current flows through the coil, it creates a magnetic field, and the polarity of the magnetic field, north and south, is determined by the direction of current through the coil. So what happens is the magnetic field created in the coil will be repelled or attracted to the permanent magnet that surrounds the coil. So the pole piece will be forced out or forced in, depending upon whether the electricity is positive or negative. And as shown in figure 3, when we apply an alternating current to the coil, then the pole piece will be constantly moving in and out. The rate of motion of the pole piece is determined by the frequency of the AC, and of course the distance that the pole piece moves is determined by the magnitude of the positive and negative peaks. So as we supply an AC voltage to the pole piece, or to the coil, the pole piece moves in and out, and this will recreate in sound energy or sound waves the AC voltage that is sent to a coil of wire. So we've seen how we can convert sound waves to electrical energy. We can convert the motion of a steel string into electrical energy. And of course, we can convert the electrical energy back into sound waves.